All right. So first, next week is the lab exam. So to get ready for that, be sure you know how to do the problems in all the labs. And remember, it's cumulative, so you have to go back and make sense out of the ones in the for the first exam too. All right, so whichever one you want to come, either one's fine. So it's just like in your lab section, but you can go to either one. Okay, so we were talking about yes. Nope. Yeah, right. Maybe today we'll get to that. Yikes. No, we still don't have any, but hopefully by the end of today you'll be able to work on some. Okay, so how do we know force directions? And we broke up forces into, and these forces that I'm talking about are the contact forces. And there are two types. There's going to be a third type that we'll talk about pretty soon. But for now, two types. The first one is pulling force. And we think about that involving cables and pulleys. And then the second type is pushing contact along a flat surface. We've done the first one, and now we have to do the second one. And then most problems will have forces of each of these types in it. So pushing contact along a flat surface. So some problems that have this kind of contact force are if you have a box sitting on the floor or sliding along the floor and we don't have any friction, or if you have like a cart with wheels on the floor, or if you have let's say two carts that are touching each other like that. This contact force between the floor and this box is pushing contact along a flat surface. They're each pushing on each other. This is pushing contact along a flat surface. And then in this example, we have it there, there, and we also have it here. Those two boxes are pushing on each other where they're touching. So when two objects are pushing on each other along a flat surface, the direction of the force is perpendicular to the surface of contact. And toward the chosen body, away from the contacting body. Okay, so for example, if you have a cart resting on the floor, and let's say this has a mass m, and say that the body we choose to isolate is the cart. The forces acting are first the weight force, that's mg down, and then second you have contact along this flat surface. It's perpendicular to the surface, so this is the surface of contact. We know that the force is perpendicular to that, so it can be either up or down. Those are both perpendicular to that dotted line. And we want the one that's toward the chosen body, away from the contacting body. So do we want up or down? Up, yep. And you can call that whatever you want. It's often called N for normal force. Normal means perpendicular, so it's called normal force because it's perpendicular to the surface. Okay, so let's use this in an example problem. So let's say that we have a cart sitting on a surface, and let's say that the cart has a mass of 1 kilogram, and let's say that we apply a force to it of 10 newtons that way. And we want to figure out two things. First, what's the acceleration of the cart? And specifically, let me just say this explicitly, that what's the acceleration vector of the cart? And then second, what's the contact force vector applied to the cart by the ground. All right, well, the body we're going to choose to isolate is the cart. So there's the cart. And now let's think about the forces acting on it. There's a weight. That's 1 kilogram times 9.81, so 9.81 newtons down. There's a pushing contact on the wheels, and that's perpendicular to the ground, toward the cart, away from the ground, so up, and I'll call that N. And then there's the force that we were given that's applied to the left of the cart. And I'll use the usual orientation of the coordinate system. So now we'll go to Newton's second law. And add up the forces. This 10 Newton force is in the positive x direction. So that's a vector of 10, 0. The 9.81 Newton force is in the negative y direction. So that's 0, negative 9.81. And the contact force is in the positive y direction, so that's 0, n. And that's all the forces. And if you add up all those forces, it has to be equal to the mass of the chosen object, that's 1 kilogram, times the acceleration vector. There's one thing that we know about the possible accelerations. Remember, accelerations are changes in velocity. So can this thing change velocity side to side? Yeah, it can. I mean, it can roll this way or that, and that velocity can change. If it's rolling along a flat surface, can it change its up and down velocity? No, that's the thing that it can't do. The y component of its velocity is 0 no matter what it's doing this way. And so that stays the same. And so we're going to write this acceleration vector as some unknown x component of acceleration and 0 y acceleration. And so the thinking here is that it can accelerate along the x-axis, but not the y-axis. To accelerate along the y-axis, it would have to jump off the ground or sink into the ground, and it seems like a reasonable assumption that it's not going to do that. Okay, so this gives two equations. The x component of this equation says 10 plus 0 is equal to 1a. And you can solve that for a. Well, it's sort of already solved. A is equal to 10. And now the y component of this equation says 0 minus 9.81 This school gets super loud at 6. Is it only on Wednesdays when the... It's like quiet all day when there's like 40,000 people here. Okay, so the y equation says 0 minus 9.81 plus n is equal to 0. So algebraically solve for n, and we get that n is equal to positive 9.81. Okay, so part A asks for the acceleration vector. We've already specified the acceleration vector. Remember, the acceleration vector appears in Newton's second law. So this is it. The only problem was that when we put it into Newton's second law, it wasn't complete because we didn't know what that A value is. Now we've figured out what that is, so we just have to plug it back in here. So the acceleration vector, A, is equal to A0, which is equal to, A is equal to 10, so this is 10, 0. And what are the units of acceleration? Yep. And then for B, we're looking for the force vector applied to the cart by the ground. That's this one. That's the force on the cart by the ground. So that's equal to 0n. Plug in the n value and you get 0, 9.81. And force has SI units of newtons. Any questions about that?
So the acceleration y is 0 because of velocity?
The acceleration is 0 for y because it's just not moving at all in the y direction. It's only moving along the x direction. So if it's not moving at all along the y direction, the velocity is 0 the whole time. And if the velocity is 0 the whole time, the velocity isn't changing, and so you can't have any acceleration. Okay, let's do one now where we have two objects pushing against each other. So let's say the one on the left is 10 kilograms. The one on the right is 15 kilograms. What? Yeah, that's true. It has heavier stuff in it. And let's apply a force of 50 newtons to the one on the left. And here's what we want to figure out. First, we want to figure out the acceleration vector of the carts. their velocities are always going to match, so their accelerations have to match. So the acceleration of one is the acceleration of the other is the acceleration of both of them together. And then second, we want to calculate the force vector applied to the 10 kilogram by the 15 kilogram. Okay, so first we want to calculate the acceleration. And so to do that, we're going to choose as an object both of these two things together. Okay, so like, is that allowed? Well, if I'm going to do it, then probably. But it might seem sort of weird at first that we're allowed to do that. But remember, even when I isolated this cart here, that's made up of a body and wheels. Those are separate things. And I lumped them all together. So yeah, you can lump different stuff together. Even if it was all one solid piece, it's made up of however many atoms and subatomic particles and stuff, you know. So you can lump multiple things together. Okay, so here's the chosen object. And now we have to figure out what forces are acting. This object has a mass of 25 kilograms, and so the weight is 25 times 9.81, which is 245.25, I think. Is that right? Okay. And then there's the applied force of 50 newtons on the left. And then there's a pushing contact. I'm going to lump it all together and just call it, you know, this force that's applied on to all these wheels. I'm going to treat it like it's just acting at one place, and I'll call that N.
So the normal force of flow is to whatever is touching the ground. Like it has to be to the wheel, not just to like.
Yeah, that's right. Well, you know, right now, where we apply these forces doesn't matter. I think it's a little clearer if you do it that way, just because it's easier to tell what that force represents. But as long as we're dealing with particles, remember there's no difference between one point or another. We're treating like everything is just acting at a single point. So where you apply it doesn't really matter, but it'll matter later when we treat things as rigid bodies. Okay, so Newton's second law says this 50 Newton force, that's acting in the positive x direction, so that's 50, 0. The 245.25 is acting in the negative y direction, so that's 0, negative 245.25. That normal force is in the positive y direction, so 0, positive n. And all of those forces have to be equal to the total mass, 25, times the acceleration that we know is only going to happen along the x-axis, so a0. So the x equation says 50 plus 0 is equal to 25a. And so if you solve for a, you get 2 meters per second squared. And if you plug that a back into the acceleration vector, you get an acceleration vector of 2, 0 meters per second squared. Any questions about that first part? So remember, Newton's second law says add up all the forces, that's equal to the mass times the acceleration vector. So the acceleration vector is this thing that's in the dotted orange. We just didn't know yet what a is. And once we solve for that, we could plug it back in and get the acceleration vector numerically. Okay, and then the y equation, well, this problem doesn't ask for that, but the y equation says 0 minus 245.25 plus n is equal to 0. We could use that to solve for n. So n is equal to 245.25. Okay, so we did part A, but part B asks for the force vector acting on the 10 kilogram by the 15 kilogram. And notice that nothing in Newton's second law says anything about the force on the 10 by the 15. And so we're going to have to choose a new object to isolate, a new chosen object for this one. So we can't find the force on the 10 by the 15 if we isolate the two together. So this time we're going to isolate the 10 kilogram. Isolate the 10 kilogram cart by itself. Okay, so the chosen body is the 10 kilogram cart. The force is acting on that. There's a weight force. This time we're only looking at the 10 kilograms, so that weight is 10 times 9.81, 98.1. We have a pushing contact from the ground that's acting up. That's not the same as what I called N before. I'll just give it a different name, N sub 10. It is a normal force, but it's a different one. It's not the whole thing. And then we have the 50 Newton force that's applied on the left. And now there's one more force acting on the 10 kilogram cart. What's that? Yeah, that's the pushing contact from the 15. That force is going to be perpendicular to the surface of contact toward the chosen body. So that's this way. And I'll call that R for reaction. You know, that's just a variable name. You could call it F for force. And now we'll plug this into Newton's second law. The 50 acts in the positive x direction, so that's 50, 0. The 98.1 acts in the negative y direction, so 0, negative 98.1. The N10 acts in the positive y direction, so 0, N10. And the R acts in the negative x direction, so that's 0, that's negative R, 0. And if we add up all those forces, that has to be equal to the mass of the chosen object, 10, times the acceleration vector of the chosen object, which is the same as the acceleration of the whole system from before. So what did we get for that? 2, 0? That's the acceleration vector from part A. So now the x equation says 50 plus 0 minus r is equal to 20. And so r, let me not skip any steps here. So we have 50 is equal to 20 plus r, if I add r to both sides, then subtract 20 from both sides, and you get 30 is equal to r. This vector here represents the force on the 10 by the 20, by the 15. All we have to do is substitute in this value for r. And so the force on the 10 by the 15 is equal to negative 30, 0. Yeah, right. I mean, mathematically it's negative because we had a negative in this formula for the force vector, but the reason we add that negative is because in this drawing of the chosen body, it was acting in the negative x direction. Okay. So the next thing I want to do is talk about a certain kind of diagram that's going to be helpful in these kind of problems.
I have a quick question.
Yes?
So we get the same answer if we were looking for the force on 15 kilograms by 10?
Yeah, that's a good question. You'd get the same magnitude, but the direction would be opposite. So, yeah. But we'll talk about why that is pretty soon. Okay, so the next thing we have to talk about is free body diagrams. I'm going to abbreviate that as FBDs. And from now on, you have to draw a free body diagram for every use of Newton's second law. And the purpose of a free body diagram is just to make it, okay, so it makes it very clear what's the boundary of your chosen object, and what forces are acting on the chosen object. I've already, when we use Newton's second law, been doing something that has kind of the same idea as the free body diagrams. I always drew the chosen body and then drew all the forces acting on it, and that's basically what a free body diagram is, but there's going to be some rules about how to do that. So here are the steps for drawing a free body diagram. First, draw a closed outline of the chosen body. The reason you want a closed outline is you want to be really clear to yourself about what things are inside the package that you're calling the chosen body, like when we isolated the two carts together. We want to draw an outline of that to say everything inside this outline is the chosen body, and we want to be really clear what's not included. Okay, so that's the point of the outline. This outline should have no internal details. Or outside objects. So, for example, if you're isolating a person, you don't really have to draw the fingers and stuff, but okay, so that's a closed outline. Stick figures, you know, that's not, okay? Also, what about this? No, because there's nothing to be smiling about. No, because the face is internal details, okay? The whole point of this is just to be clear about what the boundary is between your chosen body and the stuff that's not your chosen body. And then what about that? No, because the grass is not included, and so that just shouldn't be in there. Okay? These are all no, no, no. Really, those should say nor, I think. So that's the first step. And then the second step is draw a downward arrow and label it with the object's weight. And then third, at each place where the boundary makes contact with the outside world, or where the boundary makes contact with the surroundings, draw an arrow in the direction of that contact force. And label it either with a variable or a numeric value for the force. So a variable or a numeric force value. Okay, so let me just do a couple example problems that put all this stuff together. Any questions yet? Bless you. Okay, so let's say that there are two boxes sitting on an elevator. 2 kilograms on the bottom and 1 kilogram on top. And we want to figure out first what's the force vector applied to the 2 kilogram box by the elevator. And second, what's the force vector applied to the 2 kilogram box by the 1 kilogram box? And let's say the elevator is accelerating downwards at 3 meters per second squared. Okay, so for part A, we have some choices about what to isolate. If we're trying to figure out a force on the 2 kilogram box, the first thing that should occur to you is to isolate the 2 kilogram box. It turns out that won't work in this case. But let's try it. Well, I shouldn't have told you that, because now it's not very, like, you don't really want to try it. You want to do the right thing. But okay. So for part A, we can't do it by isolating the by the 2 kilogram box. And the reason is we have too many variables. Watch. Okay, so I'm going to draw a free body diagram of the 2 kilogram box. So there's the outline. There's a weight acting down of 2 times 9.81. And now we're just going to mentally go around the boundary, looking for places where the surroundings make contact with the boundary. One of those places is at the floor, where the elevator touches it. That's a pushing contact along a flat surface, so that force is this way. And I'll call that Fe for force from the elevator. And then if we keep going around the boundary, we get to the top, and there's contact with the boundary from the 1 kilogram box. That's a pushing contact. So perpendicular to the surface, to that flat surface, toward the chosen body, so this way, down. And I'll call that F1. Are there any other places around the boundary where anything's touching? No. Not on the 2. Okay, so Newton's second law says, well, that F1 is in the negative y direction, so 0, negative F1. Plus 0, negative 19.62. Plus Fe is in the positive y direction, so 0, Fe. Is equal to the mass of the chosen object, 2, times the acceleration. The acceleration is given as 3 meters per second squared in the negative y direction. So that's 0, negative 3. Okay, so we have 2 equations. The first one, the x equation, says 0 plus 0 plus 0 equals 0. So that doesn't help us. And then the second equation says negative F1 minus 19.62 plus Fe is equal to negative 6. And here's as good as you can get. Negative F1 plus Fe is equal to positive 13.62. And now you're stuck. We've used everything we can from these equations, and we still have 2 variables, and you can't use a single equation to solve for 2 variables. See, I told you. See, I told you. I told you. Okay, so what do you want to isolate? That didn't work. That's not so bad. Like, you isolate one thing, it didn't work. That's fine. You learned something, and yep.
Would you combine the weight of both options?
Yes, that's exactly what we're going to do. So we're going to isolate the 1 and the 2 together instead.
I have a question.
Okay.
Where did the F1 come from? Like, where is that force?
That's the pushing force applied to the 2 by the 1. Okay, so free body diagram of the 1 and 2 together. Okay, so outline looks something like that. You know, no internal details, just an outline of the whole system of things you're isolating. And then the weight. What's the mass of the chosen object? 3. It's the 2 and the 1 together. Okay, it's not funny. So that's 29.43. And then there's contact with the boundary at the bottom. That's this force applied by the elevator. And now go around the boundary. Are there any other places where the surroundings touch this object? Nope, that's it. So by choosing carefully what we isolated, we got rid of that other force that we don't want to know, at least for now. Okay, so Newton's second law says 0, negative 29.43 plus 0, positive Fe is equal to the mass of the chosen object, 3, times the acceleration of the chosen object, 0, negative 3, and so we have an x equation that says 0 plus 0 equals 0. Doesn't do any good. But the second equation says negative 29.43 plus Fe is equal to negative 9. And so Fe is equal to positive 20.43. What? Newtons, yep. That's a force. And so now we just have to plug that back into, you know, this is the force applied by the elevator. So now we just, so now I'll just plug this back in there. Let me just write this answer down. So the force vector from the elevator, plug that 20.43 in for the Fe, and you get 0, 20.43 newtons. Yep.
So last time we had said tension is always positive, but the force doesn't always have to be positive.
This pushing contact also has to be positive.
Pushing. So anytime you're doing a free body diagram, you're using force, you're thinking that it should be positive.
Yeah, the variable needs to come out with a positive answer. The vectors can have negative components because those are directions, but the variable needs to be positive. Okay, so now part B. Now we want to figure out the force on the 2 by the 1. We can't isolate the two of them together anymore because the force we want to calculate doesn't come up in the equations, you know. So now we have to go back to that original one, isolate the 2 kilogram, and so now we're going to isolate the 2 kilogram. And everything we did before is still valid. You could just go back and use that, but I'm going to write it all again. So free body diagram of the 2 kilogram. We have the weight of 19.62. We have that force Fe, and now we know what that value is. So Fe is equal to 20.43. And then we have that pushing force down, I'll call it F1, from the 1 kilogram box. So Newton's second law says 0, negative 19.62, plus we have 20.43 acting in the positive y direction, so that's 0, 20.43. We have F1 acting in the negative y direction, so that's 0, negative F1. And all of that's equal to the mass, 2, times the acceleration, 0, negative 3. So we get an x equation that's useless, but a y equation that says negative 19.62 plus 20.43 minus F1 is equal to negative 6. So negative 19.62 plus 20.43 plus 6 is equal to F1. And I can't do that in my head. So what do you get for F1? 6.81. Now this is the force vector on the 2 by the 1. So the force on 2 by 1 you get from plugging 6.81 back in here. And so you get 0, negative 6.81 newtons. Any questions about that? That's a lot. Well, let's do one more problem. You want to try one? Yeah, why not? Can't hurt. Okay, so let's say we have 2 carts connected by a cable. So 1 kilogram connected to a 3 kilogram. And there's a force applied to the 3 kilogram of 20 newtons. And so first, we want to calculate the acceleration vector. And second, we want to calculate the cable tension. Okay, so for part A, let's just do part A first. Anybody have a feel for what we want to isolate to calculate the acceleration? Yeah, you want to combine them. If you isolate either one of them individually, you're going to have that thing happen where you have too many variables. You won't know the acceleration and you won't know the force applied by that cable. So for part A, isolate the 3 and the 1 together. Okay, so take a couple minutes, work together on that, see if you can get through that one. And then I'll go through it in a... Okay, so... Okay, so there's the outline. This has a total mass of 4, so the weight is 4 times 9.81, 39.24. Yeah. And then there's a pushing force up from the ground. So I'll call that maybe N total. And then keep going around the boundary, and the only other place there's force from the surroundings is the 20 newtons that were given. So Newton's second law says that 20 is in the negative x direction, so negative 20, 0. 39.24 is in the negative y. N total is in the positive y. And this is equal to the mass, 4, times the acceleration that can only happen horizontally, so that's a 0. And so the x equation says negative 20 is equal to 4a. So a is equal to negative 5. And then if you plug that into this vector to get the total acceleration, the acceleration vector is negative 5, 0. There's the y equation too, but we don't care. That doesn't give us anything that we're asked for.
So for A there, since we're going the negative x direction, it's not negative A though?
That's right, because since we, wait, that's not negative, what? Oh, here? Like, why did I put this just as positive A there? Because you don't have to try to guess what it's going to do. In some cases, like in this case, it's easy to tell which direction it's going to accelerate because there's only one horizontal force. But at other times, and there's no reason to guess because that negative will work out by itself if it's negative.
Okay.
So just treat it positive. If it comes out negative, then that's... Okay, let me just do part B. So for part B, now we have the acceleration. We have to isolate one of these two carts. Which one do you want to isolate? Well, it turns out it doesn't matter. And no matter which one you isolate, you'll get the same answer. Well, that's good. It would matter if they gave different answers. It's sort of cool how that works, actually. You know, like So now I'm going to isolate the 1 kilogram, say. So watch this. So isolate the 1 kilogram. So there's a weight force of, oh, and I'm going to do what I said to do before, include a little stump of that cable. Okay, so there's a weight of 9.81. There's an upward force, I'll call it N1. And then there's a cable force T. So what about that 20 Newton force? Why isn't that in there? Did I just forget? It's possible. Yeah, because that's touching the boundary of the 3 kilogram one, so it doesn't appear on this one. If we isolated the 3 kilogram one, it would appear. So how could it be that, like, when we go through these calculations, this one that doesn't have that 20 is going to give us the same cable tension? You know what I mean? Isn't that weird? Do you believe me?
And then we would have the tension going.
The tension would go the other way. We'd have a 20. We'd have all this different stuff going on, and the answers would be exactly the same. It's cool. It's like physics magic. Okay, so Newton's second law says negative T0 plus 0, negative 9.81 plus 0 and 1 is equal to the mass, 1, times the acceleration that we just calculated, negative 5,0. And the x equation says negative t is equal to negative 5. So t is equal to 5 newtons. I thought you were doing that bottle flipping game.
No.
Okay, let's do the other one. Okay, you twisted my arm. Free body diagram of the 3. Because I'm afraid that you're not going to believe that. Like, how could this possibly work? Okay, so here's the 3. Little stump of the cable. So there's a downward force of 29.43, an upward pushing force from the ground of N3, this cable force to the right that we're trying to calculate, and then the 20 Newton force. Okay, Newton's second law says negative 20, 0, plus 0, negative 29.43, plus 0, N3, plus positive T0 is equal to 3 times negative 5, 0. And so the x equation says negative 20, negative 20 plus t is equal to negative 15. And so t is equal to 5 newtons. Mic drop. So, like, how does it even know that, I mean, none of this would accelerate at all without that 20 Newton force. How did this one even know that there's a 20 Newton force? Yep.
So I have a question.
Ah.
So, for part B, this first part of the
Mhm.
question or whatever. So why isn't there a force pushing? No, for the top one.
Yeah.
Yeah. So why isn't there a force pushing perpendicular to T, basically?
Is that on the 3 kilogram one?
You don't see what I'm saying?
Why isn't this T pushing on this?
Nope.
Okay.
So if the box is traveling
Mhm.
in the negative x direction, why isn't anything pushing on the 1 kilogram box?
Well, instead of pushing on it, the cable's pulling on it. I think if the thing is a cable, then it's pulling, and it follows the rules of pulling. And how to know whether there's forces acting on something, the way to do it is to just be consistent about just, all you're doing is going around the boundary looking for contact. If there's no contact, there's no force. Okay, so like how did like nothing would move at all if there was no 20 Newton force. How do we isolate the 1 kilogram? Yep.
Acceleration factor?
Yes, that's right. So the reason that the way that this one knows that there's a 20 Newton force is that in Newton's second law, we're using this acceleration that we got from isolating the two together. So we are using information that 20 Newton force is there. Okay. I will. So now you can work on some of the problems. I'll look at which ones and put on D2L like which problems you're ready to do. All right. Have a good weekend. If anybody has questions, I'm going over the lab right now, so I'd be happy to answer questions.